All right, so this exam is over chapters 21 and 22. The logistics are same as usual. It's going to be roughly 10 to 12 questions, somewhere in there. Some multiple choice, some calculation based. Roughly one third are multiple choice or conceptual based points. The other two thirds are calculation based. And you do get partial credit for doing as much work as you're able to on problems that are not the no work required ones. So if there's a calculation and you're not sure how to do it, please still write something so that I have something to grade. If you leave it blank and move on, there's just nothing I can really do with it to give any points back. So just keep that in mind, and you can get extra points even if you are not sure how to answer a problem. You can again bring a cheat sheet. It can be one side of an 8.5 by 11 sheet of paper with whatever you want on it. For this exam, that probably would be things like the right-hand rules and lenses law to remind you how you do them. Maybe some examples, that sort of thing could be good. But I'm going to start by just going through some of the notes and just pointing out what's the big important bits. And then I'll look at some example problems. So first thing in chapter 21 is this idea about what has to be happening for a charge to feel a force in the first place. This is before you even get to the actual right-hand rule stuff. Your charge has to be moving to feel a force in a magnetic field. If it's not moving, there's nothing to even worry about the right-hand rule for because there's no magnetic force. The charge also has to be moving at least a little bit perpendicular to the field. If it is moving along the direction of the field or exactly opposite that direction, it's still not going to feel a force. So again, there's no point even applying the right-hand rule. You can, if you forget that, kind of realize it and catch yourself when applying the right-hand rule. And I'll get to that when I start talking about different examples of it. If the charge is moving and it is moving at least a little bit perpendicular to the direction of the magnetic field, then we can use the right-hand rule to figure out how the force acting on the charge will point. And so that rule is going to be your thumb is the velocity, the fingers are the magnetic field, and your palm determines the direction of the force. That force will be away from your palm if it's a positive charge and towards your palm if it's a negative. So when we look at these examples, it will be good to kind of approach every problem as if it's a positive charge. And then if the question happens to be about a negative charge, just take your answer you got and flip it. So this is probably a good spot to show some examples of this. All right, so let's say we have a charge that is moving upward in a field that points to the right, and I want to know the direction of the force on that charge if it's a positive charge. So it is moving upward. Notice I start with my fingers kind of curled up because I don't know which way they should point just yet. All right, the field is pointing to the right. So away from my palm would be that way, into the screen or into the page. If it was a negative charge, I would just flip that over and it would be out of the page. The mistakes I see with this, I've realized over time, is one, my hand stays flat. You can't do this. You also cannot bend your thumb in any other way except to bring it closer to your fingers. This is allowed, that is not, and this is not. You have to kind of treat your hand like it's wooden, and the only hinge it has is one to just kind of bring your thumb in and out. If you don't do that, you start getting some strange directions with the right-hand rule. You also have to be using your right hand. All right, so that was the first example. Charge moves up in a field to the right. That leads to a force into the page for a positive charge, out for a negative. Another example, let's say a charge moves into the page in a field that points downward. It moves into the page in a field that points downward, and you can see I'm bending my wrist, that's okay, but my hand is staying flat. So into the page in a field that points downward. Hopefully you can see that for a positive charge, my palm is facing to the left. A positive charge would feel a force to the left. A negative charge would feel a force the opposite direction, so to the right. Some more examples. A charge is moving downward in a field that points into the page. Charge is moving downward, field points into the page. Away from my palm would be to the right, so that's the force on a positive charge. Towards my palm would be the force on a negative, and that would be to the left. One where this wouldn't work. Say I had a problem where a charge is moving up in a field that points down. So charge is moving up, but the field points down. I can't get my hand to do both at the same time. I'd have to break my thumb to make it point up at the same time. That's a hint that something's off here. The reason is the answer is zero force in that case, because the charge is moving this way, the field's this way, the charge is moving along the magnetic field, and so it doesn't feel a force. The right-hand rule can't help me with that, and that's why it seems to not be working. Another example like that. I have a charge that's sitting stationary in a field that points into the page. Okay, I know what to do with my fingers, they're into the page, but the charge is stationary. So what does my thumb do? I don't know. That's a hint that the answer is the force is zero. There is no direction for it. And the last one is charge is moving up, let's say, in a field that points up. I can do that, up and up, but this is the only example I've seen of this where my thumb is not kind of splayed out. It's with my fingers. That's again telling me something's different about this case. And it's because the charge is moving this way, the field is pointing this way. Zero force on that charge. So those are your three cases where it's not the right-hand rule, it's the thing about the charge doesn't feel a force. So let's say a charge is moving, let's go down, while the field is to the right. The charge is going down, the field is to the right, and so I see that my palm is facing me. That's out of the page, out of the screen. So that would be the direction of the force on a positive charge, is sort of out towards you. On a negative charge, it would be into the screen. So the right-hand rule is the hard part. The easy part is actually calculating the size of the force. It is just going to be take your charge, whatever it is. If it's a proton or electron, you use that 1.6 times 10 to the negative 19 coulombs number. You take the speed of it, you take the field strength, and then the angle between the direction the charge is moving and the field. All those things are pretty much just fed to you in the problem. They're given, and you just put them all together to tell me the size of the force. That usually doesn't cause a lot of problems. It's the right-hand rule stuff that really gets people. For this page, the main takeaway is about the circular motion of the charge, that it sort of veers out of the magnetic field, and that's covered in more detail, I think, on the next page. But also that magnetic fields don't speed up or slow down charges. They can redirect them, but that's about all they can do. Electric fields can do speeding up or slowing down, but magnetic fields, all they can do is change the direction of a charge. On this page is where we saw that to find which circle a charge moves along. This is the kind of question I could ask. How you answer it is, say we got a charge moving to the right in a field that points into the page. In that case, like we've got in the picture above, that will lead to a force that is upward. And what that's going to do is make the charge, even though it's initially going to the right, it's going to start veering upward. And that gives you enough information to kind of have an idea of what the circle will look like. You can sort of complete it from there. And I may ask you something like that, like what is the path the charge follows as a result of this magnetic field? You draw in the circle. There are also questions where it's like, do we know if this is a positive or negative charge based on the circle it's following? To answer questions like that, if you apply your right-hand rule and find that the force you're getting points towards the center, then it's positive. If you find that the force points the other way based on the right-hand rule you did, it's a negative charge because you should have assumed the force would be the other way in the first place if it's a negative charge. So if things feel backwards when you do it, it's a good chance it's a negative charge, is what I'm getting at. Again, that's the hard part. The easy part is the math. If I ask you for the radius of that circle, it's just that formula right there. And when we get to currents, it's actually the same stuff as it already was for individual charges. There's actually no new information for currents. It's just making it more convenient. So we still use the right-hand rule to figure out the direction of the force on a current. The only real modification is the formula to find the size of that force. And it's actually just a rewriting of the force on a single charge. So treat the current stuff as pretty much the same as individual charges. And actually, it's even a little bit easier because for currents, you only use conventional current flow. You don't actually worry about which way charges are really moving or whether they're positive or negative. You just always go with the direction of current I told you about, treat it as positive, and then away from your palm is the direction of the force. For loops of wire, you can get a torque, you get a rotation of the wire. In that case, to figure out which way the wire will rotate, I really think the easiest way is to just apply the right-hand rule to both sides of the wire, like we did here. And you imagine pulling on the wire like that. Which way is it going to rotate? Hopefully you can see, similar to if you had a steering wheel and you were pulling on it like that, that's going to steer the whole loop clockwise. And that's how you can figure out the rotation of it. That'll stop when we get to this point where the wire itself is perpendicular to the field or its normal is aligned with the field. And that's because once you reach that point, you're kind of just stretching out the loop. It's like pulling outward on both sides of your steering wheel. It's not going to turn it, it's just going to stretch it. Again, that's the hard part, the direction stuff. If I ask you for how much torque, that's easy. Just plug and chug. And that's chapter 21. Chapter 22, we run into the second right-hand rule. And we use kind of two versions of it, one for a straight wire and one for a coil or loop of wire. They're actually the same rule, but it's kind of easier to apply them as if they're two separate rules. So the idea of the second right-hand rule is you bring something like a pencil, which hopefully you'll have anyway. Current is still your thumb. The direction charge flows, still your thumb. The field is still your fingers. But now it's the field being created by that current. This is not the force on charge. This is a field created by charge. That's the difference between right-hand rule 1 and right-hand rule 2. If you want to know force on the charge, that's 1. Field of the charge, that's 2. All right, so the idea here is if I grab the wire, my fingers will wrap around it in a certain direction, and I can see that they're wrapping around like that. That's usually where people stop and think they've got the answer to the question. There's one more step, though, that is being left out here. And that's that I'll usually ask about, okay, so what's the direction of the field, say, over here, or over on the other side, or in front of the wire, or back behind it? In that case, you have to think about, well, which way is the field pointing right there? I know it's circulating around, but right here, that means it's out of the page towards you. If I keep circling around right here, that means it's to the right. If I keep circling around over here, it means into the page. And if I circle around back here, it means to the left. How you can get those directions right, at least what seems to have worked so far, is imagine on that circle, it's like a roundabout. You're driving around and around and around the wire. Which way are you facing at each of those points? That's the direction of the field. So if you're driving around, by the time you get to here, you're facing out this way so that you can keep driving and turn until you get to here. Now you're facing to the right. If you keep going around, now you're facing into the page, and you keep going around, now you're facing to the left. If current's flowing the other way, your thumb is now facing the other way, and your fingers will wrap around the other way. So now the circle, which I'm kind of running out of hands for this, now the circle is going around this way. And in that case, to answer, you still think about, all right, I'm driving around and around and around. When I get over here, which way am I facing? Into the page. Over here, I'm facing to the right. To the right of the wire, I'm facing out of the page. And then out in front, I'm facing to the left.
Just to clarify, so let's say I'm facing like in front of, well, no, I'm like in front of the wire, so I'm turning left
Okay, so like you're here.
Yeah, so I'm turning, no, I'm facing left.
So if we're wrapping around like this, you would be
Oh,
facing
the
the
other way.
left.
I was talking about the other way.
Okay, so here, you mean like this? So in front of the wire, I interpret as like right here.
Mm-hmm.
So in this case, my fingers are wrapping around like
Oh,
that.
that. Okay.
And so right here, I'd be about to go off to the right.
Oh, okay.
Yep.
Okay. I got it.
The only twist there really ever is on this is it could be that the current is flowing out at you. So there would be a dot saying current's flowing out that way or into the page. So there's a cross saying it's going into the page. It's still the same idea, but now, for instance, this case, the dot coming out at you, the field is circulating around like this. So I kind of have to imagine I'm driving up a wall, I guess. Here, I'm about to go this way, so the direction is down. If I keep going around here, beneath the wire, I'm about to go to the right. If I keep going around here, I'm about to go up. And if I keep going around up here, I'm about to go to the left. Or vice versa, if I reverse the current flow, now the circle is going around the other way, like that. So up here, I'm about to go to the right. Here, I'm about to go down. Down beneath the wire, I'm about to go to the left. And off to the left of the wire, I'm about to go up. So again, that's the hard part, is getting the direction of the field right. The strength of it, plug and chug. I give you a current, I give you how far you are from the wire. You put all that in, you're done. It's possible I give you two wires, for instance. Someone asked about a question related to that, but then you just do this process twice. And figuring out the direction is the hard part. That determines whether you add the fields or subtract them. So I'll get to a question like that here in a bit. For a loop of wire, for that, you're going to want to have a roll of tape or something circular, and you're free to bring that to the exam. So the idea here is your thumb is still saying which direction current's flowing, and that's going to be either counterclockwise, so around that way, or clockwise, around the other way. To know which way the field points as a result of that current, I grab on, so this would be counterclockwise, and then I grab the tape itself, which my fingers are struggling a little bit with, but actually this shows it even more clearly. My fingers are pointing towards you, out of the page right now. If I had to grab the wire so that my thumb wrapped the other way, now my fingers are pointing away from you. That would be into the page. The only variants on that are instead the loop is facing like this. So say I have current flowing around this way, sort of up through the front, down through the back. Okay, I wrap my thumb in the way that current flows. I grab on. My fingers are pointing to the left. That's the direction of that field. If instead I've got current flowing the other way, going up the backside and down the front, my thumb needs to grab on like that. I grab onto the wire. That's a rightward facing field. Or if I have the loop oriented like this, let's say current's going around left to right on the front, right to left on the back. I grab on, grab the loop, my fingers point up through it. And last, if I have current flowing right to left on the front side or left to right on the back, I grab on like that, dip my fingers through, and you can see my fingers are pointing down. That's pretty much all possible cases, but I would not recommend treating it as a bunch of different cases and trying to memorize or write them all down and hope that that lines up with the picture I give. Instead, if you get really used to the rules, you just kind of get it right every time, and you don't need all that extra information because that's what the right hand rule is for. It covers all possible cases. If you want to find the strength of the magnetic field at the center of a loop, plug and chug. Whatever current you're given, however many loops, however large the radius of the loop, that's all you need. The only thing that sometimes trips people up here is if it's a single loop of wire rather than a coil, This number n is just 1. N equals 1 for a loop. If it's 100 loops, it's a coil made up of 100 loops, n is 100. But usually people forget that when n is equal to 1 for a singular loop. This is the kind of thing I was talking about where I say I could give you two different objects and I ask for the net magnetic field, but the idea is you separately figure out its direction for the straight wire and then for the loop, and then the net field is just you add them if they're in the same direction, you subtract if they're in opposite directions. They could actually be at several weird odd directions even besides that where you'd need vector addition, but I'm not going to do that to you on this exam. So this is the full extent of like the kind of problem you could see. If you have something like a solenoid, it's actually still just the usual rule for a single loop. Pick out any loop in the solenoid and see which way current's flowing through it. So I see current sort of flowing up through the front, down through the back. That's a case we already covered. It's a field pointing to the left. So don't treat solenoids as if it's any different from any old loop. And if you need the field strength for a solenoid, it's that right there. What usually trips people up with this one is little n is not the same as big N. Big N is how many loops. Little n is how tightly they're packed, and you find that by dividing the number of loops by the length. So if you see that it's a number of loops, you know that's big N. If it's 100 loops per meter, that's little n, because that's how tightly the loops are packed. Chapter 22. The nice thing about this chapter is it's all talking about one law, and that's Faraday's law. It's just looking at all the little different aspects of it. So I'm going to jump to Faraday's law. It's this right here. It says that if you have a coil or loop of wire and you change how much magnetic field is passing through that coil or loop, you'll get an EMF. Effectively, it's like a battery got attached to that loop. And we usually talk about that in terms of which way current flows through the loop. To figure out that direction of current flow, that's Lenz's law. So that's the stuff we'll get to here in a minute. But the strength of the induced EMF, the battery you get, depends on how many loops you've got, how much the flux changed, and how quickly it changed. Flux can change because you changed the field strength, the size of the loop, or the orientation of the loop. So if I ask for the induced EMF, you use this. If I ask for induced current instead, it still works like it did for regular old circuits. The induced current is the induced EMF over the resistance of the wire. It's V equals IR. It's just now these are some strange magnetic sort of currents and EMFs instead of the ones we're used to from batteries. But in effect, that EMF pushes current and that current flows through the wire. So past that point, it works the same as any old circuit. So this is actually, I think this was an old exam question. So I will give you some situation where I change something about the loop, either its orientation, its size, or the field it's sitting in, or I just yank it out of the field. That's like changing the field strength to 0. And whatever case I give, you just calculate the EMF that's induced. You figure out what's actually changing. In this case, it was theta. And so I found change in cosine of theta. And that's about it. Plug and chug. The hard part is direction. So Lenz's law says nature hates it when flux changes. It does not hate magnetic fields. And so it's not always trying to cancel out magnetic fields. It's trying to cancel out changes that happen. So this example is a really good one for it. Also, the ones that have been in the pre-lecture and homework stuff are good practice for Lenz's law. They may be ones that you just kind of brute force clicked through because they only had a couple choices, but now would be the time to go through and make sure you understand how the answer is what it is. So if I look at this problem, we started out with no flux through the loop, and all of a sudden there is flux. We've got a bunch of field lines poking through that loop, sticking into the page. Nature says, I don't like that. Put it back the way it was. Its only option to do that is to create its own magnetic field. And in this case, it's going to point out of the page, all these little dots, because it's trying to oppose that sudden increase of field lines into the page. It's trying to cancel some of them out with an outward-facing field. How can it do that? With a current flowing through the loop. And that current flows according to the second right-hand rule, but in reverse. So what I mean by that is, in this case, I figured out information about the field first. I figured out which way my fingers should point out of the page. Based on that, I need to think about which way my thumb has to grab the tape. In this case, like that, so that current flows counterclockwise. So it's in reverse because we're used to saying, here's the current, what's the field? This is, here's the field, what's the current? That's really the only difference compared to all the right-hand rule stuff we already did. And that says in this case that the current flows counterclockwise. We come over to the other side. Now our loop is exiting the field, so it has lots of field lines poking into the page, and all of a sudden none. Nature doesn't like that kind of change either. So in this case, it sees that we lost a lot of field lines, it tries to put them back. And so the induced field points into the page. How does that happen? Through an induced current flowing clockwise, because to get a field that points into the page, my finger is dipping through into the page, I have to grab the loop like that with my thumb wrapping around clockwise. So that's why we got a clockwise induced current. In the middle, we don't have an induced current because it's just moving through the field. It's got just as many field lines poking through at one point in that field as anywhere else in it. So there's no change in flux. There's nothing for nature to hate. It doesn't hate the field, it hates changes. And it's always trying to fix up changes in flux. For the generator, it's still, if I ask like which way does current flow in a rotating loop, you already know how to do that from what we looked at up above. Just look at a case like this one. You look at whether the flux is increasing or decreasing. In this case, as we rotate the loop, we're going to lose field lines. We're going to catch less of them when the loop is something like that. And so nature tries to put them back. In this case, the induced magnetic field must point to the right because it's trying to help out the original field. In order to create a field that points to the right like that, current has to flow sort of top to bottom on the front side of the loop. So we need a field that points to the right. My thumb touches on to the loop like this, meaning current is flowing like that. All right, and that is Lenz's law. If you have a generator, I'll usually state it as a generator, and then you're given all the stuff you need to calculate. The only thing that is sometimes forgotten there is if I give you a value in hertz for the frequency, that's F. Omega is 2 pi times that. It's the difference between regular frequency and angular frequency. If I give you something that's already in radians per second, that's angular, you're good to go. But if I give you something in hertz, you have to do that extra step of 2 pi f. And last, mutual and self-inductance is actually still more of the same. The hard part is figuring out the direction of current flow, and this is the hardest one because there's the most steps. So if we look at this picture on the right, and I'll just clear all this away. This is a case where I have some current flowing in my primary coil. Let's say it suddenly starts flowing this way through it. How much and which way is the current that's induced in the secondary coil as a result of that? Well, this current, which I'll call I1, is going to move down through this coil of wire and around and around and around. If I use my second right-hand rule, I can figure out that if current is flowing down like that, when I grab on, my fingers point to the right. And so that current's going to create a magnetic field that points to the right. Something like this. And it will extend out past the coil to some extent. So we might call that B1. Okay, but now the secondary coil is suddenly seeing a magnetic field. The flux through it has changed. Nature doesn't like that. It says, oh, there's all of a sudden all this field pointing to the right through me. I want to put things back the way they were. So I want to oppose that change by decreasing the number of field lines poking through. The only way I can do that is create a field pointing to the left so that it cancels out some of the original red field. That would be what we call the induced magnetic field. So how can we get a situation where the magnetic field is pointing to the left through this coil? Now I know my fingers have to point to the left, and so to grab onto the loop, my thumb will wrap around like that. And so current will flow this way. That is the induced current. And I could track that back to see that it flows up and up, just to see how much, or how it flows through every loop. But that is the idea there. For self-inductance, it's the same thing. You just think of the secondary coil as actually the primary coil is serving as both things now. What I mean is take all this stuff we just did for the secondary coil. That's also what's happening within the primary coil because it's seeing that sudden change in flux because of this red magnetic field. And so it says, I don't like that sudden change. And so there's a field induced that points to the left. And so that means current should flow this way through the primary coil as well. The only issue is current was already flowing this way. So which way does current actually flow? It's the difference between those. It's this. And so you get it's sort of like a resistance to current flow, but it's now a magnetic resistance. We call that back EMF. It lowers the effective current you get when you do this sort of procedure. And that's used in a lot of cases because you want something to start up slowly. You call it a soft start. And so you don't want to feed too much current to it at first. You can achieve that by having something with a lot of back EMF that'll ramp up over time until you get the full current. Math-wise, though, I ask you how much EMF is induced. Plug and chug. I give you things like M. It's the thing that's measured in henries. Or if I'm talking about a single coil, it's actually the same exact formula, but now we use the letter L instead. Still measured in henries. And that is pretty much the chapter. I won't ask you to calculate inductance. I will give it to you if I have a question like that. Any questions at this stage? All right, well, I do have a few over email. All right, this one, we've got two long straight wires separated by 0.12 meters. They carry current in opposite directions. Find the magnitude of the net magnetic field at the points labeled A and B. So for this one, because it's in a perspective view, I would probably personally redraw it so that it's not anymore, so that it's sort of a head-on view. That could be me looking at the top. That could be me looking at the sides. I have a few options. I'm going to go with me looking at the sides, sort of down the barrel of the wires. If I did that, I would see one wire with current flowing into the page and the other with current flowing out at me. So this one is the one I'm seeing go into the page. This one I'm seeing come out towards me. And then A would be over here, and B would be here. I'm going to call this wire 1 and this wire 2, so I can distinguish between the fields. It asks for the magnitude of the net magnetic field. In order to be able to answer that, I have to know which way each field is pointing. So wire 1, it's current going into the page. I grab onto the wire, and that means the field circulates around clockwise. But at any particular point, what does that mean? Well, if I'm over on this side of the wire to the right of it, I'm about to drive down this way. I'm facing down. If I'm down beneath it, I'm about to go to the left. If I'm off to the left of it, I'm about to go up. And if I'm up over top, I'm about to go to the right. So let me sketch that in. So for wire 1, the field sort of circles around, something like that. It's not a very good circle, but the idea again was down to the left, up to the right. So at point A, B1 is upward. At point B, B1 is downward. All right, now I got to do the same stuff for wire 2. It's out of the page, and so you could probably guess that that means all the field line directions flip. Let me just show that real fast. because I don't want you to rely on pattern recognition for this, because you may not be given two wires and you already know the direction of the fields for one. You need to be able to do this in isolation for each one. So in this case, the current's coming out towards you. I grab onto the wire. That means the field circulates around like that. So over here, I'm about to go up. If I keep going up to the top, I'm about to go to the left. Over here, I'm about to go down. And then down here, I'm about to go to the right. So that's how this field circulates. Something like that. And so I can see that at point B, wire 2's field points down. Point A is not caught in that circle. It's going to be a bigger circle because it's further away from wire 2 than point B is. I imagine like this field actually is many circles, concentric circles, that all do this. All have this sort of behavior. Eventually there will be one circle that's so large, it does pass through point A. And there we would still see the field point downward. And so what we find is that at point A, B1 and B2 are in opposite directions, and so would subtract from each other. At point B, they're in the same direction, and so they add to each other. It looks like what happened here is the person got it when they added together, but didn't get it when they subtracted. And that's usually how it goes. It's because the net field is not always just add the two numbers. You got to think about their directions. And if you got a negative, it's possible you just subtracted the bigger one from the smaller one, and they wanted smaller from bigger. The wire carries current of 7.1 amps in both cases, but point A is far away from wire 2. It is closer to wire 1, and so wire 1's field will be stronger. This one will be the stronger of the two fields. And so the net field should also point upwards, which we would call a positive. So I think the issue was mainly that negative there. For this one, it's mostly just knowing what flux is. So you could think of flux in terms of that equation, but if you know what that equation is counting, this problem becomes a lot easier. What we designed this equation to count is the number of field lines through a surface. And if I look at it that way, I don't even really need to do any math for most of these parts. For the flux through the front, clearly there's no field lines passing through that face because they're all going off to the right. So of course the answer is 0. For the back face, clearly there's no field lines passing through. So the answer is 0. For the flux through the bottom surface, no field lines passing through that either. So the answer is 0. When I get to D and E, now there is field lines passing through. So D is asking about this surface, and E is asking about this back surface. In the hint for this question, I said to do E first and then do D. The reason I said that is because for E, meaning this back face, it's catching those field lines head on. In other words, the angle between its normal direction, this way, and the magnetic field itself, the red vectors, it's technically 180, but it's going to be 1 for the cosine. It's cosine of 0 or 180. It's going to be 1 or -1. And so that just determines the sign of the flux. It should technically be negative for this back face because the lines are poking into it, and it should be positive for the front face because they're sticking out. But it looks like Wiley does not make that distinction. So we really just need to calculate, all right, the flux through the back face is BA cosine theta, and that is 0.28. The area is 0.3 by 1.2, and then cosine of technically 180, but 0 will get you the same magnitude, the same sized flux. And if you calculate all that, you should get that number right there. If you had these values, if you have different values, it's a slightly different number. And the reason I said to do that first is because, well, look, just as many lines are going into the back face as are coming out of the front face. So of course the front face must have the same amount of flux through it as the back face. I don't even need to do any more math to do that. You could, but then you got to think about if this is like a side view, my field lines are coming through like this. Now I do have to think about the angle between the normal to that face, the perpendicular to it, and then this field. So I got to think about what is that angle? And that looks like some geometry that I don't really want to do. And so I didn't. I took the shortcut of knowing what flux is. If I did want to do it this way, I'd have to say, let's see. I could find this angle through doing some trig, because I know the opposite and adjacent sides. So I could do inverse tangent to find this one. I'll call it phi, just some other variable, because I don't know that it's the same as the angle theta just yet. But what I can say is if that's phi, so is this. And then that phi plus this 90-degree angle plus theta has to add up to 180 because they're along a straight line. So phi plus 90 plus theta equals 180. Or if I solve that, I can say theta is 90 minus phi. So whatever angle I find down at that bottom right corner, I just subtract it from 90. That'll give me the angle I need to use to find the flux. That's the math way. That's worse. Don't do it that way. I have a few more from someone else over email, and they're about questions in the practice exam. The questions were about 5 and 8. They say, I understand that charges have a circular path and that negative and positive charges flip the direction of the path, but I'm having trouble working these problems. Would be helpful to see a quick refresher on how to do this. Okay, so if I look at 5, it shows two charged particles. They have the same speed. Which one is negatively charged? So yeah, this is the one I was getting at of try it, and if the force you're predicting points towards the center, it's a positive. If it points the other way, then it's a negative because it should have pointed towards the center to make this thing move in a circle. So to show this, we have a field that's pointing out of the page, and we've got one charge that at least at this point shown that I chose to look at, one of those charges is moving down, the other is moving up. Let's see what that says about the force each should feel. So if I have a charge moving up in a field that points out of the page, so for that, I kind of have to wrap around a little bit. There's not a comfortable or easy way to show this, to be honest, but it's going up out of the page, and so that charge should feel a force to the right if it's positive. But if I look back at my picture, because it's moving in a circle with the center off to the left, it's actually feeling a force to the left. That disagrees with what my right-hand rule says. That must be the negative charge. If I looked at charge 1 and tried the same thing, it was moving down in a field that's pointing out of the page, which, again, doing my best with this, that would say my palm is facing to the left for a positive charge, and that agrees with what it needs to do in order for the force to be towards the center of the circle. So particle 1 is a positive charge. Things are working out for it. All right, if I come to 8, I know that the charges are feeling a force to the left as they enter this region because that's where the circles are. They're deflected off to the left when they enter. So I know enough about the velocity, which is my finger, and I know about my palm, which is the force, and I know they're positive charges, so I don't have to flip the direction of the force. So if I come back to this screen for a second, I know the charges are moving up, and in this case, I know which way my palm is facing. I know that it's to the left, and so I can see that my fingers point into the page, and that's why the answer is into the page. All right, another question was about number 12. So this question was, why does it say right-hand rule 2? That is because that is a typo. It should say right-hand rule 1. Because as they say in this email, it's asking about a force. That's how you know this is right-hand rule 1. So sorry for the mistake there. This is still right-hand rule 1, and we can apply it by saying it's showing current kind of going down at an angle like this, and it's showing the field sort of to the right. This is again getting a little uncomfortable, but you can see my palm is facing out of the screen. And for current, you don't have to worry about positive or negative. It's always assuming positive charge because that's the conventional current that they're showing you. All right, so that's how I got out of the page. Next one was number 16. Confused on the setup of the word problem. It's wording. So a compass is placed on the ground. A wire carrying a large current from east to west is placed above the compass. The end of the compass needle. All right, and the question was just sort of like, what is the perspective of this? It is that the compass is like underneath. You're a bird looking down at the wire, and there's a compass underneath it. And the question is, what's it gonna do? To answer that, you have to think about the field created by the wire. And this is our second right-hand rule. So I'll come back over here. We've got current flowing to the left. We grab onto the wire. That tells us that the field circulates like this. And I'm asking back here, because that would be where the compass is from that view. Back here, which way is my finger about to go? Down, or in terms of the directions given, north, south, east, west, that is to the south. That is why I say it will point to the south. That does assume that the field strength is actually stronger than the Earth's magnetic field, because otherwise you're dealing with one field pointing north and the other pointing south, and you need the difference between them. So we do have to assume that the field from this wire is stronger. I'm guessing that's why they said large current. Okay, and then number 18, the question was, would we get points off for not including the negative? I'd say it depends, because what it depends on is how you're defining your directions in the first place. I think of out of the page as the positive direction in this case, and so I get a negative answer to tell me that it's into the page is the actual direction of the net magnetic field. If you think of into the page as the positive direction, then you would get a positive number here, because you would have said this thing is positive, B2, whereas B1 is negative, and you would have gotten a positive here. But that would be telling you, again, into the page, but you chose that as the positive direction. So would I count off on that? I would, if my problem had some axes predefined, in the sense that I might say something like take out of the page to be the positive direction. Because in that case, by saying negative, you are specifying into the page. But more likely, I probably would ask magnitude and then ask you to just tell me the direction. So tell me that it's into the page, and then the magnitude would just be the stuff in the box. Do we have any other questions? If not, I will see y'all on Monday. Enjoy your weekend.